The presentation should be starting shortly. We were having tech issues, per usual. Because why wouldn't we have tech issues? So I do need you to be quiet-ish because I'm unmuted. There we go. Now I'm.
All right, sorry about that. Trying to figure out what happened here. There was an error in the CBC meeting link for some reason. Hi, I'm Dr. Cardona, and I'm one of the presenters today. I'm also trying to manage the people who are coming in at the same time because my partner is going to be a little late. I'm about to pin the interpreter so that anyone can see the interpreter as they speak. So as I said, I'm Dr. Cardona. I am the virtual events coordinator for the Community Book Connection. If you are not aware of what we are as an organization, we are a committee of faculty that democratically elect a book to be selected for that year, the academic year, to be used in many classes and across any discipline. And this year's book was one of the top 3 finalists, which everyone at CCBC was able to vote on. And the winner was Under a White Sky by Elizabeth Kolbert. This book is all about environmental issues, including climate change. So every chapter covers a different topic. And today we have a group of faculty that will be presenting on climate change as it relates to Under a White Sky. So to start, Dr. Anna Jaworski will begin, and then she'll talk about the causes of climate change, followed by Dr. Jenny Allen, who will talk about the consequences, and I will wrap up with a direct discussion of the book and how this relates to the content in Elizabeth Kolbert's book, Under a White Sky. Go ahead, Anna.
All right. Am I getting an echo? Christina? No echo? Can people hear me?
We can hear you, and there is no echo. I had muted
Excellent.
myself.
Yeah, beautiful. All right. So starting off here, let's start with a quick discussion of what exactly is going on. Hopefully you all know that the planet is getting warmer, but by how much is it getting warmer? And so this little visualization from NASA is very helpful for kind of visualizing how global temperatures have changed over the years. So Christina, if you could hit play on that. So as we watch this, we see that in the 1800s and the early 1900s, temperatures were hovering right around average. We weren't seeing much change, right? So you see that, oh. All right, let's play that again. There we go. So it's hovering right around 0 degrees C. That means there isn't much change. All right, so temperatures were fairly stable. They were hovering around a little bit cooler than average to about average. And as we watch, right as we start to approach the 1930s here, we start to see the temperatures are going above. We're seeing a warming. And as we watch, we see that that rate of warming gets faster over time. In the 1950s, we're seeing warming. We're seeing warming. So we're going out from this 0 degrees Celsius, 1970s, 75. There we go. Now we're seeing a lot of warming. There's the 90s, well above average temperatures now. 2000s, it starts to go faster. 2010, 2012. And as you can see, as we approach the 2020s, we are getting about 1.5 degrees Celsius than we were in the early 1900s. So this is showing about 1 degree Celsius on average. It says about 1.5 degrees Celsius warmer than the planet was in the early 1900s. And one of the things I like to point out to people is they say, well, 1.5 degrees, that doesn't sound like a very big number. And you're right, it doesn't sound like a very big number, but it's winter now. And I want you guys to think, does it take a lot of energy or a little bit of energy to get your house warm in the winter? All right, it takes a good bit of energy to warm your house up a few degrees in the winter. Now imagine you're warming the entire planet up 1.5 degrees Celsius. So that's a lot of energy required to change the temperature of our entire planet. So that 1.5 degrees may seem small, but it's actually pretty big. Go ahead, Christina. We can also see this here. We can see on the left-hand side here from climate.gov, we see how annual temperatures are differing from the average. And we see starting right around the 1980s, that temperatures start to get drastically warmer each year. And we can also look at it on the globe, where we see overall, we're seeing pretty significant temperature changes from the early 1900s. So that's where we are currently at. And what do you guys think? Before we switch slides here, is Maryland experiencing warmer temperatures, cooler than average temperatures, or is Maryland not changing? Why don't you guys throw that in the chat? What do you think? Is Maryland generally getting warmer? Is Maryland generally getting cooler, or is Maryland staying the same? Throw it in the chat. And my students who are in my classroom, if you think it's warmer, put your hand up. If you think it's colder, put your hand down. Very good. My students say warmer. All right, let's go to the next slide, please. All right, and here's Maryland. This is showing Maryland's average temperatures from 1895 all the way up to 2021. And on average, Maryland is also getting warmer. And so you're not imagining it. Okay, Maryland's average annual temperature has increased by 4 degrees Celsius compared to the early 1900s. All right, so, but what is causing this? Next slide, please. All right, so as we look at this graph here, this graph can be a little complicated. And what this is showing you natural drivers of climate change and human drivers of climate change. Okay, and the blue line, Christina, can you hover over the blue line, please? The blue line down there, that's showing you how temperatures should look if it was only natural drivers of climate change. So natural drivers of climate change include things like solar flares and volcanoes. Okay, the red line, which is a little hard to see, is showing you human drivers of climate change. So if we were only looking at human drivers, the red line would indicate what temperatures should be. All right, so the blue line shows what temperatures should be if it was only natural drivers. The red line shows what temperatures should be if it was only human drivers of climate change, which we'll talk about in a second. And then the orange line combines the two. But then we also have the black line here. The black line is showing you the actual temperature. Okay. So this is what we've actually observed. And so the other three lines, we developed those lines by building models. So basically they built models in which they took all of the natural factors and they said, okay, if it was only due to natural causes, how warm will our planet be? Well, if you look at that blue line, it doesn't in any way match the actual temperatures. There's a big discrepancy between how warm our planet would be with only natural causes and what our actual temperatures are. So the blue line and the black line, they don't match. And what this tells us is that it's not really natural factors. That's really not what's driving climate change. But if we look at the red and the orange lines, those really match up with what we're actually observing in terms of temperatures. So most of modern day climate change is caused by humans, or anthropogenic. So anthropogenic means referring to humans. So most of what we see, these temperatures can mostly be explained by human drivers of climate change. And does anyone know, can you throw it in the chat, what's one big way in which humans drive climate change? There's a number of different ways of saying this. What do you guys think? Can anyone throw it in the chat? Fossil fuels, very good. Fossil fuels, thank you. This is from my students in meteorology. So go ahead, Christina, go to the next slide, please. Okay. So both Sam and I think that was Israel mentioned fossil fuels, right? And so when we burn fossil fuels, we release greenhouse gases. Can anyone name some greenhouse gases? If you can name some greenhouse gases, throw them in the chat. Can any of my students in the classroom name a greenhouse gas? Say it out loud. Carbon dioxide, methane, very good. So those are greenhouse gases. What greenhouse gases do is they help keep heat in the lower atmosphere. So if we look at this, the left-hand side of this image, it says natural greenhouse effect, right? We want a natural greenhouse effect because that's what keeps our planet warm enough to live in. However, today we are experiencing what we call an enhanced greenhouse effect. Basically, we're adding blankets to our planet. And as we add more carbon or more fossil side, more greenhouse gases to our atmosphere, those greenhouse gases trap more heat and enhances the greenhouse effect. It makes it stronger. Therefore, you can see that it's more red on that side. So our planet is warmer with an enhanced greenhouse effect. Whereas the natural greenhouse effect keeps it just warm enough to be comfortable. An enhanced greenhouse effect starts to get uncomfortable. And this enhanced greenhouse effect is the result of adding a lot of extra greenhouse gases to our atmosphere. Go ahead, Christina. All right, I was looking for images and I found this from NASA. And it says here, can you tell the difference between caffeinated and decaf coffee? Of my coffee drinking students, who can tell the difference? I don't have many coffee drinking students. Who drinks soda and can tell the difference? Okay, well, of my coffee drinking students can tell the difference between caffeinated and decaf, right? And the reality is there isn't that much caffeine in a cup of caffeinated coffee, okay? And so you might think, well, there isn't that much caffeine, I would never notice it, but you do. And the point NASA is trying to make here is that while it doesn't look like there's that much extra carbon dioxide, it still has a big impact, right? So small changes in the amount of carbon dioxide in our atmosphere, which is a greenhouse gas, result in big temperature changes. Now, if we go to the next slide, we can actually see this. So if we look at this slide, we're seeing changes in temperature, and this goes back 800,000 years. Students in my class, you're going to see this figure again in a few weeks. And then the blue line is showing changes in atmospheric CO2 concentrations. And as you can see in Earth's history, as CO2 has gone up, so has temperature. Right? When CO2 goes down, temperature goes down. Well, if Christina zooms into the modern time, or moves her mouse to the modern, where it says current, there is a lot of carbon dioxide in our atmosphere. And yeah, it's only changed by what? About 200-ish parts per million? Right, 200 parts per million may not sound like a lot, but in the grand scheme of our atmosphere, it has a big impact. And so we expect, the change from before, I guess it's about up 420, thank you. So it's up about 420 there. It may not seem like a lot, but that is a lot of carbon dioxide, and we expect temperature trends to follow after that. Now you'll notice temperature hasn't risen quite as fast as CO2, and that makes sense because there's a little bit of a delay in how temperature responds. We expect to see a little bit of a delay here. All right, go on. All right, I'll go back again, sorry. So the primary driver of modern day climate change is the burning of fossil fuels, which results in an enhanced greenhouse effect. And an enhanced greenhouse effect means we're keeping more heat in our atmosphere, which is also keeping us warmer. And greenhouse gases include carbon dioxide, methane, nitrous oxide, and a lot of those come from the burning of fossil fuels. But it's not just the burning of fossil fuels that's causing climate change. Can anyone suggest another thing that's causing climate change? Another impact of the carbon cycle. Right? Pollution, yep, other pollutants can also enhance warming. What else? What about a landscape change? Right, okay, as we see more ice melt, that leads to a feedback loop as well. But another landscape change. More deforestation, okay? So thank you, Sam. So deforestation is another driver of climate change. But once again, that relates back to the carbon cycle. Because when we cut down trees, they absorb less carbon. when they absorb less carbon, we end up with more carbon in the atmosphere. Okay, so there's a number of factors that are driving modern day climate change, but the really big one, the most powerful one, is the increase in greenhouse gases in our atmosphere from the burning of fossil fuels. And someone in the chat just mentioned storms, which is not actually a cause of climate change, but as Dr. Allen will show, it can be a result. Whenever you're ready, Christina. Sorry about that. I had to cough for a second. Okay. So as we see here, as we experience an enhanced greenhouse effect, we see an increase in the average temperatures, and we start experiencing a new climate system. And then over the next few slides, Dr. Allen will go over the actual consequences of this new climate, which we're about to experience, or we are experiencing, excuse me. Thank you.
I was still muted. Okay, excellent. So thank you. That was a great summary of the issues that we're experiencing. So thinking about, now that we know that the planet is warming, what are some impacts that everybody might think we're experiencing? Why don't you throw some things in the chat? Everybody can hear me, right? Okay, hurricanes, wildfires, health problems, droughts. Excellent. Good. So there are a lot of impacts from a warming planet. In the interest of time, because I could spend hours talking about it, I'm only going to focus on a couple of the most important impacts that we're starting to experience. So the first being changes in weather patterns. So we know the temperatures are increasing around the planet. And so with warming temperatures, we're going to see more evaporation, which means more water vapor in the atmosphere. So what does that mean? Well, if we have more water vapor in the atmosphere, when it rains, we're going to get more intense rainstorms. And that's going to lead to increased risks of flooding around the world. Also more runoff, which accumulates and increases the risk for the flooding. So that's a major impact that we're already seeing, these more intense rainstorms. Warmer temperatures also, again, more evaporation means drier soils. So that puts us at risk for a higher risk for droughts. So again, that higher intense rainstorms that we're seeing means that that water is running off the ground immediately to streams, rivers, whatever the closest water body is, instead of sitting and soaking into the ground. And if we have drier soils, warming temperatures, it puts certain particular areas, even more that were already vulnerable to droughts, even more at risk for droughts. So that's going to be a major issue. Next slide. So somebody, I think it was Jason, mentioned hurricanes, and that is absolutely right. So another thing that we're seeing are more extreme storms. More water vapor in the atmosphere leads to more active hurricanes. The Atlantic season in particular has become more active. 2020 was a year of a lot of issues, but one additional issue was that it was the most active hurricane season in the Atlantic Ocean. We had 30 named storms, which broke the record from the 2005, which had 28 storms. So 30 storms. Another major record that was broken that year was in Nicaragua. Previous to 2020, they'd only had 4 Category 5 or Category 5, which is the worst of the hurricanes, the strongest of the hurricanes, had made landfall in that area. And in 2020, if you remember, there were 2 that hit just in 2 weeks. So it was pretty catastrophic for that area. And so, again, we're seeing the warming temperatures in the atmosphere leads to warming ocean temperatures, which the warming temperatures is what is going to increase the severity of the storms that develop. And in addition to that, we already know there's more water vapor. So if you add in the warming temperatures, the severity of the storm, more water coming in when it hits land, the real concern with these increase in hurricanes is not necessarily the wind, but also the impact from the storm surge or the amount of water, the flooding that happens, especially if some of these hurricanes recently have been coming in and then sitting on land for a while. So they've been dumping a lot of water, and really the major impacts have been the flooding that's happening. Next slide. Okay, so another thing that we're starting to see, you may have heard, it's becoming more familiar in our everyday language, polar vortex, have been happening more often. It's a term that most of you had probably never heard of until more recently. And that's because we don't really, up until more recent times, had never experienced a polar vortex. And the reason for that is because it's what a polar vortex is. And Christina, if you could hover over, let me get rid of this meeting chat so I can see the normal circumstances. Yes, thank you. So under normal circumstances, what a polar vortex is, it's a wind current that's an air current that's keeping the cold air in the Arctic trapped up in the Arctic, combined with a strong jet stream, which comes across the United States. That helps keep those colder Arctic airs up north and helps moderate the temperatures that we see in the United States. However, with the warming temperatures that we're starting to see, the Arctic is actually warming faster than the tropics. So if you want to scroll over to the next side where it says, where it shows the Arctic. Yeah, perfect. So the Arctic is warming faster than the tropics, which because of that, there's a smaller difference in the air pressure. And as the air pressure, the difference in the air pressure weakens, that means that those air currents are going to weaken. And so what you end up with is a weakened polar vortex, as well as a weakened and slower jet stream. And so that allows the cold air to dip down further south. So normally that air, that cold temperatures would be trapped up in the Arctic. And now because the jet stream is weakened, it allows some of that cold air to dip down, and we experience these very cold Arctic temperatures. Again, if you recall, over the past few years, I don't remember I don't think we had one last year, but maybe the year before, we had these very cold temperatures that are happening. And so we're likely to see these happen more and more in the wintertime as the Arctic continues to warm more and more. 2008. Yeah, I was going to say there's definitely a few after that. I want to say it was like 2018, maybe. I forgot to check the dates to confirm. Okay, next slide. Thank you. So again, warming temperatures, another impact that we're seeing is the loss of sea ice in glaciers. So in the Arctic, you have sea ice that builds up every year across the Arctic Ocean. And in the summertime, temperatures warm up. That's normal, right? You come into summertime, it gets warmer. The ice melts back. The ice doesn't completely melt back every year, though. There's always some ice that's left. And what we're starting to see is that the amount that's left back in the summer is getting smaller and smaller. So the sea ice extent in the summer, the minimum extent of what's left when the temperature is warm, is getting smaller and smaller. It's about a 13% decrease since they started measuring it in 1980. And I didn't think there's actually a really fun infographic that shows the extent of the ice every year. That's fun to see how much it's changed. But why would we be concerned if we're getting less sea ice by the end of the summer? What are some issues that you might be concerned about that? Isn't that good? Can we do more boating in that area? Any thoughts? Animals? What's the main animal that you might think about when that lives up in the Arctic? Seals, yeah. Penguins. Actually, penguins don't live in the Arctic. They polar bears. There we go. Excellent. So You might have heard about polar bears, that they're experiencing habitat loss. And part of that is because of the Arctic sea ice, because they need that Arctic sea ice to hunt for seals. Yes, thank you. Penguins are in the southern hemisphere. That's okay. But the polar bears hunt for ice, and they use the sea ice for hunting. They sit at the edge of the ice and wait for the seals to pop out of the water to grab them. And so as they're losing some of that sea ice, they're losing their ability to be able to hunt as efficiently. They're also having to go to other areas to look for food, walking on land more or swimming between areas more. So they're definitely experiencing habitat loss because of this. Additionally, glacier mass, the mass of the glaciers that store our frozen water as ice is starting to decrease as well, which is also problematic if we move on to the next slide, because of rising sea levels. So rising sea levels is a major impact that we're seeing as a result of the warming temperatures. So as I mentioned, the glaciers and the ice sheets are melting. And where is that fresh water going? It's going into the ocean, which is causing sea levels to rise. Another concern with rising sea levels is thermal expansion. So what happens when water gets warmed up? Does anybody know? Heat is released. Anything else? It expands. Excellent. Excellent for your class. Yeah, so see, when water warms, it expands, right? So think about when you have water and you freeze it, it shrinks down into ice, and when it warms up, it expands. So if we have a large mass of water in the ocean that's warming, that water is expanding. So between additional water, fresh water coming into the ocean, and the expansion of the water in general, we're seeing rising sea levels as a result. So this figure here is showing sea level change since the early 1900s. And so from 1900 until about 1993, those measurements were all based on tide gauge data, which is good information. However, the tide gauge data is important for one particular area, but it's maybe not indicative of sea levels all around the world. And so in 1993, with better technology, we've been able to actually use satellites to measure sea level. And the way the satellites work is they essentially ping down a radio wave, which then pings back up to the satellite. And depending on the time that it takes for it to reach the satellite, you can get an idea of where the sea surface level is. And so we can see how much the sea levels, and because it's using satellite, it can get measurements all around the world, giving it a more accurate depiction of how sea level is changing on a global scale. So these are global sea level changes. And so currently what we're seeing based on the satellite data from 1993 until 2022, we're at a rate of about 3.4 millimeters per year. So we're talking millimeters. It's a very small amount in the grand scheme of things, but those changes can have pretty catastrophic impacts. So if we go to the next slide, 8 out of the 10 largest cities are along a coast. And in the US in particular, a large part of our population lives in coastal areas. And so, what was that in the chat? 3 millimeters is about 1 meter of land loss. So yes, it doesn't sound like a lot, but it can be pretty catastrophic, especially when you add in catastrophic storms, right? So this picture in the upper hand corner is from Superstorm Sandy, which had led to catastrophic storm surges. So again, when we're thinking about hurricanes and these more extreme storms that we might experience with changing temperatures, it's not just the wind that we need to be concerned about, it's the amount of water that's moving with these storms. So if you add in the amount of rainfall that's coming from, say, a hurricane, but then you also think about the water that's moving in the ocean, if we're moving more water, that's going to have catastrophic effects on the coastline. And it's going to bring in these more intense storm surges, which can be problematic if a large majority of people are living along the coasts. And so this picture down at the bottom, these two images, it's a little hard to see, but essentially it's estimating with rising sea levels, how many houses along the coastlines would be damaged or be at risk due to rising sea levels. And so by 2045, you can see Florida is kind of the largest at risk here, and then Texas as well. And by 2100, this is also projecting at the highest risks of sea level. So it'll really depend, these are just projections, but it'll really depend on how much temperatures will really change and how much water is added from melting sea ice and glaciers. But at the highest potential risk of flooding, you can see that by 2100, we're at the majority of the East Coast, the Gulf, and the Pacific coast are at high risk. And again, with so many people living along the coastlines, how do we deal with this, right? So every time it floods, do we rebuild? What are our options? Do we stay on the coast? What happens when, the tip of Florida is covered in water? Where do those people go? So these are real concerns. Next slide. So another concern, and this definitely affects us locally within the Chesapeake Bay, is this idea of nuisance flooding. And so nuisance flooding is when tides reach anywhere between 1.5 to 2 feet above the average tide. So it's essentially high tide flooding, more extreme high tide flooding. And we're experiencing more and more of those with rising sea levels. Again, there's more water in the ocean. So as the tide comes in, it's bringing in more water. And in 2017, there was a study that looked at these nuisance flooding days and how much of an impact that has on the economy and the shops and the restaurants that are located in downtown Annapolis. And they found that the losses were anywhere between $86,000 up to $172,000. And that was in 2017. Ironically, unironically, in 2021, Annapolis experienced, and so did Baltimore and everywhere along the coast of the Bay, experienced another nuisance flooding event. For Annapolis, it was the fourth largest or the fourth worst flood that they've measured. It was around 4.9 feet above the normal tide. So again, a nuisance flooding is considered around 2 feet above the normal, and this was double that. These pictures here are actually from October 21 when that happened with the flood. I see Ellicott City in there. Ellicott City is another one that's at risk. That's not generally from nuisance flooding, but from flash floods that happened from the river there. And they had very extreme flash flooding back in, was that 2017? I think that was also 2017, that they were heavily impacted. I think that's happened twice also recently. They had a really major one, and then they had one not long after that. So they're still recovering economically from that as well. So thinking about these economic impacts, actually, can you go back 1 second for me? Thank you. And just thinking about downtown Annapolis in 2017, experiencing $200,000 potential loss of losses economically wise. If we're talking about all these different, catastrophic storms, flooding, droughts, wildfires, all these impacts that are happening, what do you think the costs are associated with them? Any guesses? Throw some numbers out. About $1 billion a year. Anybody else? Okay, you can go to the next slide. So $1 billion is a pretty good estimate. In fact, since 1980, we've had 323 weather or climate disasters that have exceeded $1 billion in damages. It's getting worse. So the image here is 2021, which had an estimated 1.48 billion of disasters around the United States, which includes wildfires. There was hailstorms, tropical storms, a lot of different weather events. And if you see this table here, it looks at 1980s by decade, essentially. The costs. So in the 1980s, the cost was around 195 billion total for the whole decade. And the increases from, I think, 2010 to 2019, we were at almost $1 trillion in terms of damages and costs of repairing, rebuilding, et cetera, from the damages. And so for all those years between 1980 and 2021, the costs of these events were estimated to be about 2.2 trillion. So there's pretty significant costs associated with these disasters that we need to factor in. And so that kind of leads us into thinking about, how do we deal with this? How do we deal with these costs? How do we deal with these impacts? And so I'm going to pass it off to Dr. Cardona to continue talking about potential solutions.
Thank you. I'm sorry I typed 2008 on accident. I should know it's exactly January 7th of 2018 because it was my 1-year anniversary when my pipes burst thanks to that polar vortex.
Oh, yes. That.
So I knew the date on the dot. So
not a great way to remember it, but
not a great way. No. We managed to celebrate another time. But thank you so much, Jenny. And so now I'm going to talk about solutions because now you know the sources and the consequences of these problems. But now we need to look at what can we do about it, right? So there are 2 ways that we can approach this. One of them is to mitigate, which means to reduce carbon emissions either through laws, regulations, or some sort of enforcement by the government to cut down on industrial pollution and maybe improve automobile efficiency or things like that, versus adapting, which is just kind of saying, well, we're going to experience these changes. We should do something to prevent those changes from being catastrophic. For example, building seawalls along the coast, raising the city, like Miami actually spent $450 million to raise the city because they have so much infrastructure that would be lost to the ocean, being so close to the sea and having so much expensive infrastructure along the coastline. So these are what we call adaptive measures. So just out of curiosity, can you enter on the chat, which do you think is the better solution? Mitigating, which is cutting down on the pollution that's causing the problem, or adapting to the solutions with solutions of infrastructure building to prevent catastrophic events? So I'm seeing a couple of responses. I'll give you a moment here. Looks like an overwhelming response to mitigation and a few adaptation responses. No, in the reality, to prevent complete and total destruction, we need both. So there seems to be a stronger vote towards mitigation, which is, preventing the problem. And I've often gotten students asking me questions like, does it even matter at this point if we already got to 420 parts per million when we should be at 300 parts per million? If we do anything about it, it's too late. And the answer is no, it's not too late. We are right now at a time that's pivotal for making those changes before everything becomes too late. So right now, if we cut down on emissions and we do drastic cuts on power plant emissions, factories, and fuel inefficiency, we could see a complete reduction of these greenhouse effects so that we don't see the worst of the worst scenario. So this graph on the slide shows you if we continue as business as usual, doing what we're doing right now with almost 8 billion human beings on this planet and growing to 9 to 10, possibly billion people in the next couple of decades, what would happen? And you can see that the climate impact would be very, very drastic. But if we cut down on emissions by mitigation, which is what most of you have suggested, we would see this black line where there would be a reduction and stabilization of climate change. So it wouldn't be at the worst case scenario, but we would still see consequences of what we've already done. So then taking adaptive measures would be necessary, such as building seawalls and restructuring the city or coastal development to make sure that people don't suffer the consequences of millions or billions of dollars of losses. But since I am focused on the book Under a White Sky, the author is actually a journalist, and she interviewed scientists and all kinds of experts in the field and saw what they were doing and wrote about it. And one of the chapters focuses on the use of geoengineering the atmosphere, which is a big term. What do we mean by geoengineering the atmosphere? Does anyone have any ideas? What do you think I mean by that? What are some of the scientists that Elizabeth Kolbert interviewed suggesting that we do when we use the term solar geoengineering? Any thoughts? Well, think about what engineering means, right? You're engineering something to change what is there or how things work. I'm seeing one of the responses says to use Earth to help Earth reduce emissions in a way, right? So we're using things that are natural, but kind of, tweaking it and making it more prevalent to reduce solar concentrations that are heating up the Earth, right? Because we talked about greenhouse gases, they act like a blanket that warm the Earth, and they're thickening as we add more and more greenhouse gases to the atmosphere. But what if we add something else to the atmosphere that prevents solar radiation from coming in instead of storing it or trapping it like greenhouse gases do? Some gases, some pollutants that we put out into the atmosphere are actually what we call aerosols. And these aerosols, what they do is reflect solar radiation before they even make it down to Earth. So what some scientists are suggesting is, oh, well, we can put some of these gases into the atmosphere, or we can figure out ways to trap that carbon that's sitting in the atmosphere somewhere else so that it doesn't create this thickening of the Earth's blanket, if you will. So one of the most common geoengineering adaptive measures that people have been taking part in is known as carbon capture and sequestration. Carbon capture, you capture the carbon from the atmosphere and you sequester it, you hide it somewhere else. And a lot of European countries have been doing this for a while. For example, in this picture, this is from the textbook that we use in environmental science. They use a method to capture carbon emissions from a coal power plant and inject it to the ground. So they store it underneath the ground. An alternative method is to fertilize the ocean with iron or some sort of nutrient to make algae grow. Algae are photosynthetic organisms, so then they would be taking up the carbon dioxide from the atmosphere, and that would be reducing the amount of carbon in the atmosphere. The problem with these methods of carbon capture and sequestration is that they're very expensive. They're high energy consumers. So in order to do this, you have to produce more energy that then creates more carbon, which then would need to be sequestered again. So it's kind of a treadmill of, it doesn't end up being a complete solution. It just creates more of a problem that needs to be dealt with later. So what do we do with that carbon after it's captured? What if it leaks? What if it goes back into the atmosphere and it's not properly stored? And it's, like I said, very costly and energy consuming. So the one technique that the book covers is, as you see on this picture, a little airplane ejecting sulfur or sulfate aerosols into the stratosphere. These are, like I said, aerosols are gases that reflect sunlight so that they're not absorbing the sunlight, not absorbing the heat, but causing it to cool down by reflecting it before it gets down to the troposphere where we are. Does anyone know what could be a problem with that? Like, what naturally emits sulfur into the atmosphere that already has been seen to be problematic in other ways? So that's a two-part question. What naturally puts out sulfur, and what are the consequences of the sulfur in the atmosphere? Does anyone know? It's a big question to ask. But maybe Anna's class, you've been on top of this? Well, one thing that emits sulfur naturally is volcanoes. It comes out in the form of sulfur dioxide, but we are adding sulfur dioxide into the atmosphere through industrial practices such as coal burning for power plants, because coal has impurities of sulfur. So when you burn the coal, sulfur can come out to the atmosphere and combine with oxygen and water in the atmosphere and come back down as something that is not necessarily good. What do you think you get if you combine a sulfate and water? That could come back down in the form of precipitation. I'm trying to give hints as I go. I'm seeing one of the responses, sulfuric acid. That is correct. So this is known as acid precipitation, which could be rain, it could be snow, it could be fog, hail, it doesn't matter. Just water coming from the atmosphere full of sulfates, because water is a universal solvent. It dissolves these gases, and then you get sulfuric acid, which comes down as acid rain, or like I said, acid precipitation. And that is not good. It's not good for our health. It's irritation, causes irritation to lung tissue. It degrades limestone, marble, which is made of calcite. It has effects on wildlife, like calcite-based organisms, or even trees that die when sulfur leaches metals from the roots of the trees. So there's a lot of negative consequences to the potential idea of injecting sulfates to the stratosphere. So just to be clear, there's different layers of the atmosphere. We live in the troposphere, which is the bottom layer. The stratosphere is right above it. So what they're suggesting is take planes and put it on the layer above us so that it wouldn't cause acid rain. The problem with that is that those gases won't necessarily stay in the stratosphere. So that could create a problem. So this image shows you what I'm saying here. This is a plane flying on the stratosphere, which is above the troposphere where we live. And they're emitting aerosols of sulfate, which would then reflect sunlight back out into space before coming down here. But those gases could potentially come down to the troposphere and cause acid precipitation. Another problem with this is that this is very energy intensive. So you have to imagine that every time you take a plane to the stratosphere, you're using a lot of fuel to do this, which again causes more greenhouse gases to form, which then you have to add more aerosols to combat. So this would not be a one-time thing. You would have to continuously put sulfates in the atmosphere to control climate from getting out of hand. Another consequence of this is in the title of the book, Under a White Sky. What the book title is referring to is that if we kept on doing this, our sky would be white. It wouldn't be blue anymore, because these sulfate aerosols would disrupt the reflectivity of light, and we would see whiter skies. So we would lose these beautiful blue skies that we see now, which I know that's more of a personal preference and aesthetics, and maybe people that would be born in a world with white skies wouldn't know the difference. But there are actually further consequences from this that are worse for especially international relationships. One of the quotes from a scientist in the book says that this could disrupt rainfall patterns, causing drought in Africa and Asia. I read further into this from scientific articles, and basically what they're trying to say is, depending on where you're deploying these sulfates in the atmosphere, the other hemisphere would experience drought, because it would shift what is known as the intertropical convergence zone, which is the area of converging air that rises right now near the equator. So where two cells of warm air rise, and as it cools, it creates rain. So if that shifts to a different hemisphere, wherever it rains right now, it wouldn't rain anymore. They would have massive droughts. We know this because in the 1970s and 80s, Africa, the area just below the deserts, the Saharan desert, which is very green and luscious and gets a lot of rain, experienced massive droughts for well over a decade because of a volcanic eruption that happened in the other hemisphere, releasing all that sulfur. So could you imagine if we in the United States say, well, we are going to put, sulfates right above us to protect us from climate change? What's going to happen to the Amazon in the Southern Hemisphere? What's going to happen to the African rainforest or the Asian rainforest? Basically, there are going to be winners and losers, and whoever has money to do this is going to be the winner, and whoever doesn't have money, third world nations, will suffer and be the losers in this scenario. So it will create conflict between countries, possibly war. So not to get too, Debbie Downer about this, but there are no good solutions. When we're looking at geoengineering the atmosphere, it's not a perfect win-all solution to combat climate change. So I'm going to present some other ideas. You all can do this on your own, but simple choices like what the food that you put in your body, that food alone could have a huge impact on your carbon footprint as a human. Think about if every single one of us, all 8 billion human beings, were more conscientious about the carbon footprint through eating less meat, possibly no meat at all. If you eat cows or beef, eating cows that have been fed grass instead of corn, because the ones that are fed corn, which is most of the stuff you get in the grocery store, those cows are emitting a lot of methane. They are producing a stronger greenhouse gas and carbon dioxide through belching and flatulence because they're indigestion, because they can't eat corn. They're supposed to be eating grass. Eating foods that have less packaging. Packaging uses energy, produces greenhouse gases. Eating more local foods instead of eating food that travel a long distance, right? If you eat foods that were grown in Pennsylvania, Maryland, Virginia area, just to keep it kind of local, you're having a smaller footprint than if you're eating foods that came from California or Asia or, some other continent or country. So eating local, organic, whole foods rather than processed foods, eating less meat, all will have an impact on our personal footprint. And you can see here on this list of foods, beef by far has the biggest emissions in greenhouse gases because of that methane production, but also because they eat a lot of food. So if you eat an animal that eats food, you have to plant the food that you're going to feed them, and that uses land, harvesting uses fossil fuels, and you have a lot of resources being used overall. So you can make choices through your food that will cut down carbon footprint, as well as if you plant a tree. Believe it or not, according to these two authors who are politicians who participated in the Paris Accords, they wrote this book called The Future We Choose, Surviving the Climate Crisis. And in one of the portions of that book, they mentioned that every single one of us, if we were to plant a tree, we could slow down the effects of climate change. So could you imagine that? If we somehow managed to plant 8 billion trees on this planet, we wouldn't have the consequences that Jenny mentioned in the previous slides, right? So other things that you could do is things that not only would be good for the environment, but save you money. Small acts mean a larger wallet. Using cold water when you do laundry instead of hot water, that uses less energy. Hanging your clothes instead of drying it in a dryer. Using cloth napkins instead of paper towels. They sell these awesome reusable paper towels nowadays that are from Sweden or something like that. It's a fad, but I hope it stays. Replacing light bulbs for more energy efficient light bulbs, cutting down on your energy bill with your heating and cooling depending on the season. I can keep on going, but there's a lot of examples from just using reusable bags instead of plastic bags, or cutting down single-use disposable plastic items that would help out to prevent some of the consequences that we're we're mentioning here today. Finally, there are some larger acts. If you have money, it helps. But you know what? The cost of an electric car is going down. I know at least 2 of us on this call have electric cars, and mine is pictured here. I had to crop my husband off so he wouldn't get angry that I was showing the picture here. But this is my car. It's a plug-in hybrid, and I plug it in. And I use the solar power panels on campus to do so, which is a source of renewable power. Using more fuel efficient vehicles like a Prius that gets 55 miles per gallon versus a Hummer that gets like 5 miles per gallon. You're using less gas, less fuel, less carbon. Shop smart. Your choices, even through your food or items that you buy, you're making a statement that drives the economy and marketing, and stores shift their production to more greener sources. And of course, voting, contacting your representatives, telling them how you feel about these matters so that they do something about it. I have some pictures here. There's like, these are bar shampoos instead of shampoos that come in plastic containers, bar soap that doesn't have all that extra packaging. Lots of examples of how you can shop green. I did use up a lot of time just because we started off a little late with that mishap, but I want to open up this time for questions, and I'm going to put a link on the chat for you. Actually, it looks like Lakshmi already did that. Thank you. She put a link on the chat for you. Students, please log on and answer the survey questions. You can enter to win a $25 gift card to a bookstore. Thank you. Does anyone have any questions at this time? One of the questions is, what are some ways that our elected officials can help make change? Anna or Jenny, would you like to take this one?
Well, they can only do so much, right? But they have a lot more power than we have because they are speaking for us, their constituents, right? So if we're telling our lawmakers what we want, what's important, hopefully that message is getting passed through, that they're fighting for us on the side when they're going to Congress and when they're, passing laws or whatever it may be, that they're like, well, these are what people want. We're hearing from people and this is important to them. So they can't fight for us if they don't know what we want. That's what I would say.
Thank you. I have another question is, does recycling help? And the answer is yes, yes, yes. Even though right now China's no longer taking our plastic recycling, so we were kind of in a limbo when it comes to plastic recycling. Glass and especially aluminum is very important to recycle because we're running out of aluminum resources. And even just recycling cuts down on the energy used to mine new virgin materials, extracting them, making into something new. So 100% recycle, but just make sure you're recycling what your city or county is actually taking, because when people throw recycling, things that are not recyclable in the recycling bin, like those deli containers, the clamshells, it contaminates the stream, and about 80% of the recycling ends up getting thrown away because people threw in dirty things in there, or greasy things, or things that were not
Plastic bags.
Or plastic bags, which you need to take to grocery stores to recycle, and bins that are specific for plastic bags.
And don't put your recyclables in plastic bags because they'll just throw it all away.
Right. Any other questions? Okay. Well, thank you very much for attending. I hope you enjoyed the talk, and please go use the links that Rashmar posted on the chat for the CBC, the Community Book Connection. I appreciate your time. Thank you.
Thank you.